senhores. Nossa, ninguém falando bom dia, ainda está todo mundo dormindo. Ah, melhorou. Bom dia a todos. Nosso último dia do nosso evento aqui, uma pena, está passando super rápido. Ao mesmo tempo, é ruim, que fica, na verdade, o tempo se encurta aqui em Brasília com um congresso fantástico que a gente está tendo aqui, mas fica um sentimento de dever cumprido, é uma felicidade todos estarmos reunidos aqui. Hoje, dando alguns recados próximos, logo depois da nossa palestra magna aqui com o professor Charles Niemeyer, nós teremos 4 seminários. Primeiro seminário aqui nessa sala de edifícios altos, com personalidades internacionais, o professor Fatih, capitaneado e coordenado pelo nosso Douglas Couto. Teremos também o seminário de estanqueidade em parceria com a IB, Instituto Brasileiro de Impermeabilização. Também teremos o seminário de pavimentos de concreto com o professor Balbo, né? E também teremos um seminário que é novidade aqui dentro do IBRACON, que é um seminário de saneamento, né? Aproveitando o marco de saneamento no Brasil, com Vinícius Caruso, falando sobre esse tema importantíssimo dentro do nosso congresso. Em paralelo, logo depois dessa apresentação, teremos algumas visitas técnicas guiadas às betoneiras, né, com a Apodi e com a Votorantim, para a gente verificar, para a gente ver esses equipamentos trabalhando, na verdade. É interessante tirar algumas dúvidas deles em trabalho, vamos dizer assim, né? Então, sem mais delongas, vou chamar o professor Charles Niemeyer, o Dr. Charles Niemeyer. Ele é o atual presidente do ACI, American Concrete Institute, e também é diretor das Américas da Master Builder Solution. Dr. Charles? Just a second. Oh. Ele está resolvendo um problema técnico com a apresentação dele. A gente vai aguardando isso. E lembrando a todos que hoje a gente terá também o jantar de gala, hoje à noite, encerrando o nosso evento, né? Cereja do bolo, né, professor? Hoje à noite, para a gente também confraternizar. É muito importante a gente ter uma felicidade, a gente agregar e ter uma festa, na verdade, para confraternizar o final do nosso evento. Agora sim, o Charles. Dr. Charles, muito obrigado.
Thank you. All right. Sorry about that. I have an issue with my translation piece here, so I'll need to get another one before, questions. Yeah. Okay. First and foremost, it's great to be back at IBRACON. I know quite a few of you in here, actually, quite a lot of people, actually. And for a period of time, I used to come to IBRACON pretty much every year, for a long stretch. And then that broke off, and I think my last visit to Brazil was back in 2016. So it's really great to be back, and especially on the 50th anniversary of IBRACON. So with that, I'd like to say, congratulations. It's especially beautiful to be here celebrating with you guys, and I'd like to extend my sincere thanks to Professor Paolo Lenny for inviting me to join you on this, particular occasion. So let's begin. Congratulations. Yeah. All right. So I'm going to be talking about the role of structural engineers in the quest for carbon neutral concrete and sustainable concrete construction. By training, I am a civil and structural engineer. But then over the past 35, 36 years or so, I've been working in the area of specialty construction chemicals. So I sort of wear 2 different hats. A structural engineer who actually knows, concrete materials, basically. And as a result of that, I have some very pointed, how do I say it? Some very pointed, information on, or actually views with respect to how structural engineers, should do things, basically. So that's some of what I'm going to be sharing with you. Now, increasingly, one of the things that we find is that, concrete structures are being designed for longer service lives. I remember way back when NBR 6118 was revised. This was quite a while back, and there was a service life of 50 years in there. I don't know if it's still 50 years or it's now increased beyond 50 years. But what we find is in a lot of places, structures are being designed for much longer lives. In the US, bridges are designed for at least 75 years, and a whole lot of other structures are aiming for 100 years and beyond. So the key thing in that particular situation is we need to make sure these structures are durable, because durability essentially implies that we would have increased service life, minimal repairs, which is very critical, and also that implies a reduction in the use of natural resources. We look at the depletion of sand, for example, in India. We heard yesterday morning, during the keynote presentation, that there's a depletion of sand in India, but they still have to make concrete. So they need to look at other things, other ways of doing so. And the bottom line is what we're aiming for is an overall reduction in the carbon footprint of a structure. So essentially, durability is very key to sustainability in the concrete industry. And I think this has pretty much been what you've heard over the past 2 days, because I remember very well, Dr. Akio Kazuga basically said the same thing, 2 days ago, and then we had the same thing yesterday. So it's a common theme that you're going to hear, that durability is very much key to sustainability in the concrete industry. Now, when you talk about sustainability, it means a whole lot of things to different people. For us as engineers, we focus on durability, but then there are things that we have to be aware of in terms of what it means to other people outside of our circles. Global warming is one of the things that a lot of people equate sustainability to. Greenhouse gas emissions, water scarcity, recycling, responsible sourcing. These are all things that other people typically will focus about. And when we talk about water scarcity, it is a real thing. This was something that I just picked up yesterday, but it was a report it was something that was published back on June 27th, this year, about a severe drought, that exists in East Africa. And it's not just in East Africa. We have drought situations in a whole lot of different places. This is a US drought monitor as of October 4th, 2002. So we're talking about just about a week and a half ago. And we can see, sorry, I need to go back. Okay. And we can see that there's areas in California and other parts where we have severe droughts. Lake Mead in Nevada, for example, is at its lowest level, ever. And it supplies water to a whole lot of different areas. So water scarcity is something that we should not take lightly at all. Now, when we look at the worldwide concrete industry concerns, basically, I group them into these four here. That is greenhouse gas emissions, water consumption, material resources, as well as the embodied energy of concrete. Those are things that are some of the main concerns currently. And along with that, we have a social responsibility to use materials and to use concrete in a very sustainable way as much as possible. Now, I talked about managing, water use and the scarcity in some regions. Now, as a result of that, there are strategies that are being developed or have been developed for water conservation. And in some places, like in California, for example, they cannot use water to water, their lawns, mainly because of the water scarcity. So these are things that, we need to be aware of. Now, here's the good news. the concrete industry has actually been doing quite well when it comes to this, mainly through the use of superplasticizers or high-range water-reducing admixtures. Now, this was an analysis that I did, way back in 2008. I haven't bothered to update it. It will be even more profound if I were to extend it to 2022. But what I ended up doing was essentially doing a calculation on the mixed water savings that we get from using high-range water-reducing admixtures or superplasticizers. And it's quite significant. So basically, the annual savings was approximately 1.9 billion liters. And we're talking that back in 2008, that was about 6% of the 33 billion liters of water, that was bottled water that was consumed in the United States. That's quite a bit. Now, cumulatively, if I look at the analysis from 86 through 2007, that amounts to about 17.4 billion liters, or approximately 53% of the bottled water consumption back in 2008 in the United States. Now, if we were to do this globally, it would really be an astounding number. So that said, water-reducing admixtures essentially help to enable the judicious use of one of the most precious natural resources, in the world, which is water. And that's being socially responsible. So we need to, in as much as people talk about concrete, being, a bad animal sometimes with respect to, carbon emissions, we have to be proud of the fact that we are doing some things that are actually also helping, society. Now, that said, the construction industry's approach to sustainability typically focuses on some of these buckets that I have over here. So obviously reducing the carbon footprint of concrete is one of the key things. Another thing is using lower impact raw materials, so we don't deplete natural resources. I already talked about water reduction. Things such as labor hazard reduction are also very critical, making it safer on the job sites, for the workers, reducing waste. And then obviously durability over the lifetime of a structure, as we've been talking about over the past couple of days. Other things such as health and safety and air quality are also very much important. So with all of this, there are different options. And one of the things that we have to be very careful about is something called greenwashing, which is when people make claims that cannot be substantiated. So when it comes to sustainability, one of the things that we have to do is to be able to quantify whatever claims that we're making. And typically, this is done through life cycle assessment. Now, life cycle assessment will normally look at the environmental portion of the three-legged stool. And this is a three-legged stool that I'm talking about, where with respect to sustainability, the things that have to be in balance are the environmental impacts, the social, as well as the economic considerations. These three have to be in balance. Life cycle assessment typically will look at the environmental portion, but then in order to incorporate the economic portion, we normally would go to eco-efficiency analysis. So it's a more comprehensive way of doing it. Now, one of the things that's going on currently in terms of being able to quantify or look at different alternatives is we also have environmental product declarations, or EPDs. Now, these EPDs are nothing more than the equivalent of nutrition labels for concrete. Right now, when you go to the supermarket and you buy a box of cereal or something else, a canned produce, for example, they would have the nutrition label on it. So it's exactly what we're doing here with concrete. But instead of things such as calories and so on, we have global warming potential expressed as kilograms CO2 equivalent, and things such as acidification potential, eutrophication potential, and so on. So this is something that as engineers, we need to be aware of in terms of the quantification of sustainability. Now, we've heard talk about embodied carbon as well as overall carbon. And embodied carbon is essentially the emissions that arise from the extraction, manufacturing, transportation, and the use of building materials. So in a very pictorial sense, this is what embodied carbon entails. Everything from extraction, the energy associated with extracting materials, all the way through the construction of the building. And along with that, as Dr. Akio said a couple of days ago, we also have operational carbon. And he basically took us through the cost of all of that and so on. And that is the carbon that is associated with emissions from a building's energy consumption. Now we found out yesterday, typically people will do analysis from cradle to gate, or you can have cradle to cradle. So it depends on how the analysis is done. Most of the analysis typically would not include the operational carbon, just the embodied carbon of the associated with the particular structure. Now, why is this important? The General Services Administration, the GSA in the US, basically controls or sets policy for all government buildings. And in March of this year, they issued standards for low embodied carbon concrete and environmentally preferable asphalt. So what we have now is a situation where the government is telling us exactly what we want to do. And that's where we don't want to do that, because they will set limits that might not be what we actually want them to do. So what did they do in this case? They basically said that all GSA new construction and major modernization designs must target a 20% reduction in their buildings' embodied carbon compared to project-specific standard baseline designs as determined by the architect. So that is it. And along with that, what they ended up doing was essentially to break concrete up into three different categories. Lightweight concrete, highly strength, and a standard mix. And then, depending on the compressive strength range, as you can see here, they basically have specified the maximum global warming potential limits for their low embodied carbon concrete. The contractor is responsible for making sure that the concrete mixes that are used in the projects will meet these limits. And what do you think is going to happen? The contractor is essentially going to go to the concrete producer and pass it on to the concrete producer. But I just wanted to make you aware of some of the things that are happening around the world. I'm not quite sure what's going on in Brazil, but then don't be surprised if these things start coming up. So proactively, the question is, okay, what is the concrete industry doing? Because as I said, we don't want a situation where we're forced to do something. So we have to take the lead in some of these situations. So the GCCA, which is the Global Cement and Concrete Association, has come up with a 2050 roadmap to net zero concrete. And this is what their roadmap entails. Essentially, if we look at the blue line over here, this is what's predicted to be where we'll end up with respect to CO2 emissions if nothing is done at all. And basically, what the GCCA is saying is, there are all of these things that we can do, such as efficiency in design and construction, efficiency in concrete production, savings in cements and binders, savings in clinker production, and then this is one of the real big ones, carbon capture and utilization or storage, or CCUS. This basically involves capturing the CO2 from the smokestacks and using them, either storing them or sequestering them in one way or the other. And then there is also, as you can see, decarbonization of the of electricity, and then relying on concrete as a CO2 sink. Now, one of the issues here is, concrete, especially the concretes that we're producing now, are of much better quality. So they're not necessarily going to carbonate to the same degree as the concretes of higher Wattsman ratios that we used to have, previously. But as you can see, with respect to efficiency in design and construction, this essentially goes to structural engineers. The choice of concrete floor slab geometry and system, choice of concrete column spacing, optimization of concrete strength, element size, and reinforcement percentage. These are things that essentially fall in the lap of structural engineers. Now, the Portland Cement Association, PCA in the US, also has a similar roadmap, and very much similar to the one from GCCA, but then they call theirs the value chain, and it's the 5 C's, looking at clinker reduction, optimization of cements, concrete, construction, as well as the concrete as a carbonation sink. Now, proactively, one of the prominent concrete producers in Northern California, did a study, or got a consultant to essentially analyze your operations and come up with the carbon footprint of their operations. And to no surprise, one of the things that they found out was that 65% of their carbon footprint is due to the Portland cement. Another 17% is due to the coarse aggregates. And then, as you can see, the rest of the various contributors are all in the single digits. Now, what does this mean? Essentially, if we want to do something about reducing the carbon footprint of concrete, then we need to look at ways to reduce the clinker factor, or how much cement we're using. And a couple of days ago, Dr. Akio talked about the geopolymer that they've devised, where essentially they're using silica fume, slag cement, and fly ash in their geopolymer concrete mixtures. But these are the things that are available, and we have some other materials as well that are coming on the scene, such as ground glass as a porcelain. So all the beer bottles and liquor bottles that typically go to the landfill are now being harvested and ground into a fine powder, and that material is extremely high in SiO2 content, which is where we see for silica fume. And as a result of that, it's able to function very much like a porcelain, and porcelains, as we know, help to improve the concrete matrix through the formation of additional calcium silicate hydrate gel. So all of these materials are very, very beneficial. Now, this is one thing that I feel very strongly about, and that is, how do we assure concrete durability? And from my perspective, I've broken it down into 6 different categories, starting with having a firm understanding of concrete durability issues, and knowledge of the exposure conditions, familiarity with applicable codes and standards, knowledge of locally available concrete and materials, understanding of life cycle cost analysis, and then what I term the other factors. So let's take a quick look at some of these things. Knowledge of the exposure conditions. As civil engineers and designers, we have to be aware of the exposure condition, because then we know exactly how to not just focus on strength as we had yesterday, but then look at the durability aspects of things. So is it close to a marine environment? Is it in a heavily populated area where we have a lot of industrial pollution? Because those are two different things. In one case we have exposure to chlorides. In the other case we have carbonation of the concrete that can also lead to corrosion of the reinforcing steel. This was a cooling tower that I worked on. This was back in the early 2000s, and it's off the coast of Tampa. At the time when I was there for these repairs, the cooling tower was only about 5 years old, and they had to shut it down for the repairs because it's difficult to see in here, but all of the columns were badly corroded, and you can see over here some of the corrosion that has already occurred. And this is a cooling tower, and within 5 years it had to be repaired. Now, why was that? They were using seawater, as a cooling medium. That's laden with salt, and that was not taken into consideration in the design of the cooling tower. So again, this is where we have to be aware of where the structures are going to be. And these are some pictures from it. So you can see here all the beams and columns were badly corroded, and we were on there. We applied they essentially ended up using cathodic protection because that was about the only way they could save the structure. And we're on there applying an overlay material over the mesh that they were using as a sacrificial anode. But this was a double T beam over there. And here you can see the precessory strand in less than 5 years already badly corroded and basically lost its function. Okay. Other things that we need to be aware of, it's not just the marine environment or looking at carbonation-induced corrosion, but then also industrial applications, chemical and food processing, plants, where chemical attack, depending on the specific application, can be very, very severe. Also, soils and groundwater with high levels of aggressive salts. So we're talking about either chemical attack from sulfates, or it could be corrosion of steel reinforcement. So again, this is why we need to have knowledge of the environment. Familiarity with codes. Most of the building codes around the world now include sections on durability, maybe pirated from one country or the other. And in Brazil, you do have NBR 6118. So you should be familiar with that. Basically, Paolo Leni was very instrumental in working on the durability portion of that as well, and so on. Other things, knowledge of locally available concrete materials. How many times do structural engineers take time to find out what's available? By talking to their material suppliers and so on. Typically they don't. But producers basically need to know what concrete materials are locally available, and that can be obtained with relative ease. And design engineers need to know the limitations of locally available materials through consultation with material producers, because that tells you what you can use and what you cannot use. In North America, in the US, in some places we don't have fly ash or we don't have slag. So those are things that we have to take into consideration when we're talking about durability, designing for durability and so on. What is locally available, what can be used. Hawaii, for example, has a lot of durability issues mainly pertaining to corrosion. However, they don't have any pozzolans. They have silica fume, which is very expensive. Fly ash is cheap in a lot of places. Slag cement is relatively inexpensive compared to Portland cement. However, in Hawaii, fly ash and slag cement cost more than Portland cement. So how do you end up with low embodied carbon concrete when you're actually going to make the cost of the concrete more expensive? You violate one of the legs of sustainability. And then understanding of our life cycle cost. This was a picture of a bridge that I took in Puerto Rico. It was